Section is specifically about quadratic functions. And so, as we look at quadratic functions, this should be a fairly familiar term at this point. But a quadratic function is going to form a graph in that U-shaped curve called a parabola. And so that term is going to be used across the board for any type of quadratic that you're going to see. A little more deep quadratics, you have this line that runs down the center of your quadratic called the axis of symmetry. Just like the line indicates, that is what the graph is symmetric to. You also have the vertex. The lowest or highest point of the parabola will always be the vertex. And so when you look at this, this is going up. You'll notice that vertex is the lowest point. If this were facing down, you would see that it would be the highest point. So the first type of form we're going to talk about is the vertex form. This is in the form f of x equals a uh, times the quantity x minus h squared plus k. A couple things about vertex form. It is very easy to get the vertex from vertex form, that is hk. I do want to point out that the original formula is a minus here. So when you see that h, you have to do the opposite of what's in front of it because it was already a minus. The axis of symmetry is the same way. It is just the h there. And it is that line, that vertical line, x equals h. If that a, that leading coefficient there is positive, the parabola is going to be going up. If it is negative, it is going to be going down. And as I mentioned, if it is facing up, that vertex will be a minimum. If it is facing down, that vertex will be the maximum. So let's look at transforming these functions. That A, as we already discussed, will tell you the direction that it faces, but it'll also tell you if it is a stretch or a shrink. All right, just like we've talked about in other functions. And then if it is negative, it is going to reflect across that x-axis. So it will flip it up or down if that is negative. When you look at horizontal translations, left and right, you are going to use that H value. And again, remember, the original formula is a negative here. So use the opposite of what you see there. And then your vertical translations are up and down. That will be your K value, just as it looks, because that is a plus. I do want to point out that if you are looking to find the y-intercept on something like this, you do have to plug in a zero. So you have to do a plug in a zero for x to find the y-intercept when it is in vertex form. So for this example, they want us to transform this graph from the parent function to the given function, all right? And we'll talk about domain and range and all of that. But if you think about the original parabola, it's going to be something like this, right? And so we want to shift this around. Now, remember, this is just sketching. So we're not going to be perfect on this. A couple things. We know it is going because that A is -2, it is going to point down and it is going to be skewed a little bit, right? We're going to have um, basically a widening of this graph. And then that H is 3. You see it's a minus, but because the original, it is going to go right 3 units. And that K is a 4, so it's going to go up 3 units. So a couple things I would ask you is I would say, what's the axis of symmetry? Well, the axis of symmetry is x equals that H. What is the vertex? Well, the vertex here is that HK. And then I would ask for the y-intercept, and you do have to plug that in. -2, 0 minus 3 squared plus 4. So we would say -3 squared is 9 times -2 is -18 plus 4. We have a -14. So while we won't be able to graph that on ours, you can see that it's going to go way down there. All right, so let's then graph this. I always recommend graphing that axis of symmetry first. And so I do this dashed line here since it's not technically part of that graph. And then I'm going to graph that vertex at the point 3, 4. So 3, 4 is right here. Now, normally I would recommend graphing that intercept, but because this has kind of been stretched or pulled, it's going to be way down here. And so you're welcome to, plug in kind of another number if you want to see where it's going to be. So you could plug in maybe a 2 or a 1 just to see what would happen and so you can reflect it. So if I plug in a 2 here, then you're going to see 2 minus 3 is -1, -1 squared is 1, times -2 plus 4, I get a +2. So you'll see that when I plug in a 2, my y value is +2, and that kind of gives you an idea of what's happening with this graph. And because this is a line of symmetry, if I graph one point over here, I can just mirror it on the other side, and then I'll be able to see what that graph is doing here. Right. And so that is the sketch of that particular graph. So if I look at domain, well, domain's my x value. It's going to go indefinitely. I know it looks like it's going straight down, but it's technically going to the left and to the right indefinitely. So my domain is really all real numbers. But my range here is not going to be all real numbers. My range, remember, is my y values. My range is going to start right here at that 4 and just go down. It doesn't get any higher than that. So y is going to be less than or equal to 4 as a range because it starts at 4 and goes down for y's. So that would be how we would graph something in vertex form. So now let's look at standard form. Standard form is going to be written in y equals ax squared plus bx plus c. This is called the quadratic term because it's squared, your linear term like an mx plus b, and then your constant. Here we have a little bit of calculating to get our axis and vertex. For our axis of symmetry, we can take that b value, negate it, negative b over 2a. If we just take those numbers and do that, we will get our axis of symmetry. To get the vertex, we actually take that x value that we just found and we plug it in. And I'm going to write it like this, f of negative b over 2a. But what that really means is just plug in the x value of your axis and solve for y. So you have an xy there. Now your y-intercept's really simple. It's just 0 and that constant, because if you plug a 0 in, 0 plus that constant, that is your y-intercept here. And so y-intercept is simple with standard form. The other two a little more complicated, but still can be done. So let's look at this example. This wants us to graph this. So I am always going to ask you for your axis, your vertex, and your y-intercept. So let's start with our axis of symmetry. Remember, we're going to take that b, which is 12, and we're going to say negative b over 2 times my a value. So this is a, b, and c. So we have negative 12 over 6. My axis here is negative 2. And so I'm going to graph that negative 2 here. That's just my symmetry line. My vertex then, I'm going to take that negative 2, that's my x value, and I'm going to plug it in. 3 negative 2 squared plus 12 times negative 2 plus 8. And so, do your order of operations here. Negative 2 squared is 4, 4 times 3 is 12, 12 times negative 2, and then plus 8, you get negative 4. So my y value here is negative 4. And so my vertex is always going to be on my axis of symmetry, but it's down here at negative 2, negative 4. And then my y-intercept, that's the easy one, 0 and my c value. And so 0 and my c, it's going to be way up here. I didn't quite give myself enough room, but 0, 8. And so if you get up to that 8 up here, you can just reflect it. You see it's 1, 2 away from my symmetry, 1, 2 on the other side is the reflection. And you can see that you have this pretty sharp sketch of a graph there. And that would be how we graph something that is in standard form. So finding your axis, your vertex, and your y-intercept is always going to help you sketch these graphs. Now, you may find that you like using one or the other. And so we are going to look at how to convert these from standard form to vertex form. And then you can graph in either way that you want to based on what we've already done. So this does require a little bit of completing the square, but not to scare you. We are just going to take these first two terms and we are going to factor out that 4. So we're going to take the 4 out of both of those terms. We're going to leave a little space here. All right. And we want this to be a perfect square so that we can write it with just a group squared. The way you do that is you're going to take that middle term, that 2. We're going to take that 2, we're going to cut it in half. In this case, it's beautiful because it is just a 1. And then we're going to square it. We're going to square that 1 and then get fact it as a 1. So to make this a perfect square, we'd have to have a plus 1. And you can see that x plus 1 would give us x squared plus 2x plus 1. So if I wrote x plus 1 and squared it and did my foiling, right? X plus 1, I would get x squared plus x plus 1, which is x squared plus 2x plus 1. So that's my goal, is to make that a perfect square. But I mean, if you know anything about math, is you can't just add a 1 in there because that now makes my uh, function no longer equal. I just threw in a 1. So I have to also subtract a 1. Now, everyone can agree that if I added a 1 and subtracted a 1, I didn't add anything. And so I didn't add anything, but I'm just doing this to be able to get this function. So I need this one out of here. I need him to come out so that I have this perfect square. In order to do that, I am going to take this 4 and distribute just to that 1 to get him out. All right. So if I distribute that 4 just to the 1, 4 times -1 is -4. And now I have pulled him out of my parentheses. And now I have this beautiful perfect square. So the 4 is going to stay there. I now have this beautiful perfect square that I can write like this. And then I have -1 minus 4, which is -5. And now I have taken this from standard form to vertex form. And in fact, if you were to do word of operations here, if you were to FOIL this, distribute your 4, and subtract that 5, you would get back to this process right here. And so these are the same two functions. One is just written in standard form, one is written in vertex form. The last thing I want to talk about here is a 0 or a root. So we've talked about y-intercepts. Now we want to talk about um, x-intercepts. X-intercept is a 0 or a root. And it's basically where it crosses the x-axis, which means it's where your y value is 0. So y-intercepts is where your x value is 0. X-intercepts are where your y value is 0. And you can do this by factoring, by quadratic formula. We're going to look at factoring. But you can, because you have what we've used before, zero product property. If you factor this and you set each factor equal to 0, you have found your roots or your zeros. And so this is just a product of numbers of 0 if one of them is 0. So you cannot multiply two numbers and get 0 unless you started out with 1, is basically what this property is saying. So it says find the y-intercept and the zeros. Well, y-intercept is really easy. Y-intercept, we just plug in 0, right? So for the y-intercept, -0 squared plus 6 times 0 equals 0. Oh, our y-intercept is 0, 0. That's easy. So let's find our zeros, which can be called roots or x-intercepts. Those are all the same thing. And to do this, we make our y0, which means we set our function equal to 0. Well, how do we solve a function that's equal to 0? Well, we solve it by factoring. And so we can take out a common factor of x. We're left with -x plus 6. And then our property says, well, one of these guys has to be equal to 0. So either we have x equals 0, which we actually already knew, or -x plus 6 equals 0. Subtract 6, divide by -1, x equals 6. And so our y-intercept is 0, 0. And our zeros, or our x-intercepts, are 0 and 6. And so that is just an easy way to find certain parts of the graph. As we build these features, we are going to also build ways to graph more complicated functions as we go.